right, so this is homework for ME470, homework 1. They're going to do problem 2 here. Okay, so we have this crank handle for a manual mixing machine. We want to design it. And so, okay, so this bottom part right here, this is like a socket, right? So it like fits onto another piece. And maybe it's like I got a square shape, or it could have like a little head. It could be like a bolt head looking thing, right? It could be something strange. Who knows, all right? But anyway, this handle like fits onto the thing, and then you're going to be cranking it, right? And so like the basic dimensions are up to us. But you got to kind of like make the decision. How big do you want this handle to be? Well, they told us that the torque is like 25 foot-pounds. So, like, if the thing was 12 inches long, that means that you'd have to exert 25 pounds, at least in the perpendicular direction. Is that reasonable for a person that's working and would have to do this kind of task? If it was a child, that would be too much. If you had to do this all day long, that might be a little excessive. You might want to keep it down to maybe the 10 to 15 pound range. You need to kind of like use your judgment and the things that you know when you're making these decisions. And decisions is what design is all about. You have to make some kind of like, use something in your life. Like, have you ever picked up a 25 pound weight? All right, was that hard to do? Right? Is that too hard? I don't know. Okay, so pulling onto the thing. But anyway, you have to kind of pick what these dimensions are. You also want your hand needs to fit over the part that is part C. So maybe you want to take a ruler and actually measure out what your hand is right there. And I don't want to don't you judge me about my small hands. I don't know, but that's somewhere right around 4 inches in terms of like the width. So if you're going to make a grip for the thing, maybe make it 5 inches, right, onto the thing. But of course, the center of your hand is where the thing is acting, right? We're going to pretend that force is acting on there. So what we do is specify the material and dimensions if it's going to, with a safety factor against static yielding of 3, and we're going to use the distortion energy theory. We're going to assume that the load is at 45 degrees right there. So not only are we cranking this thing, we're actually pulling it. Now, of course, that would be like we would have all different types of orientations, but we decided maybe that we're going to be standing and kind of pulling back towards us as we're trying to pull the thing out. That maybe that was a bad loading condition, bad loading position we decided to use as the basis of our design. So here we go. So we have all of this information, and let me just bring it over to here to the side so I can write the thing up. So this is going to be sheet 3 of my homework. I don't know why that came back onto there. Okay. So sheet 3, and please focus. Come on, focus. There you go. Hocus pocus. And we're not quite focusing. Okay, so here's my name. There I am, Dr. Deal. And it is spring 21, and this is ME470, and this is homework 1. And this is problem 2. Right here, right? So we have this crank. We can make a brief sketch. We don't need to make it artsy here, but we have a sketch of this piece right here. And amongst the reasons that I've chosen to make this sort of a open-ended kind of problem is that we want to try to become better designers and decision makers. We need to be like a little bold right here. So that's going to be A, but also I want people to do their own work. So we're going to create a scenario where it's really impossible to cheat in this and just copy somebody else's work, because we're doing something that's quite different. Everyone's is going to be a little different. It better be. So there's C. I didn't dimension that very well. So we put the dimension in there. And if this is the direction of the x-axis, yes, that's the x-axis right there. And here is z coming up that way. So here's z coming up that way. Here's our force that we're being applied to there, and here's theta that's taking place right there, right? Okay, I guess maybe I should have. Very good. That line is not very good. Okay. So other things that we know is that the torque onto the thing. I mean, right? Given. Torque is equal to 25 foot-pounds, which we usually use inch-pounds, but when I said foot-pounds is often used there. And theta is equal to 45 degrees. And regular size hands, blah, blah, blah. Okay, so we want to, for the find, we want to design the crank. Maybe I should write here, crank design. Okay, well, where to start? An FBD is a good place. But we got to get some dimensions. We got to start deciding some of these dimensions right away. So I decide, let's see, decisions. All right, assume. Let's pick C to be equal to 4 inches, right? I said I didn't want to overestimate here as we're putting the thing through here, but let's see. There's 4 inches against right there. So my hand isn't really quite 4 inches. I think that could be like a good. I mean, someone with very large hands. I don't know how much bigger that they might be. Look at it. I hurt my knuckle the other day. So I'm going to go with 4 inches. Now remember that force is only 2 inches down onto the thing. So looking at this, I think another assumption that I might want to make in here is, let me maybe make the FBD. I'm going to drop down here as I'm making this assumption here, and I'm going to look down at the XZ right here. So I'm going to go X and Z as I'm looking down here. Oops. Right, okay, so there is the looking down upon this thing, and my force is like up right in there, right? So this is the force that's acting on there, and we know that this is 45 degrees right in there. So there's going to be an equal and opposite force coming down this way, down onto here. We could, if we wanted to, we could put these reactions on there, although they're not going to be necessary for us. But it's also going to be a moment right here that is going to be, so if that's going clockwise, this thing better be counterclockwise. And there's going to be a torque. That's where that torque is going to be. So we have to decide what this dimension B is going to be. That's probably one of the most important dimensions that we're going to have to pick as part of this. So what dimension should that be? Well, as I was mentioning before, what is it? What is a reasonable amount of force to be applied onto this thing? Let's say it's 20 pounds, right? That's a good thing. I think 20 pounds, if someone's going to crank onto the thing, hopefully they're not doing it all day long. But let's say that assume F is equal to 20 pounds. If that's the case, then we do the sum of the moments, right, and balance this thing out right here. And we take 20 pounds, right, and it's going to be, let's see, that negative right there, 20 pounds times, and we're going to say it the right way. It's going to be the sine of 45 degrees, or it doesn't matter with the cosine or sine of 45 degrees. It doesn't really matter. And and then plus the 25 foot-pounds. Right? I go 25, but it needs to be foot-pounds that are applied onto the thing. Whoops, I forgot to put in times B, right? Because that needs to be there. All right, so plus. Sorry, that's counterclockwise, so that's positive. That 25, and turn that into inch-pounds right here. So what is B going to be equal to, right, onto this thing? Well, I say it's going to be, 20, you can't see my calculator from there. That's okay, you don't need to see what's on my calculator. 20, 45 times the sine, so times that. All right, so I have 25 times 12, boom. So I divide that, and I say the B needs to be 21.21 inches long. Let's make it 20 inches long. 21 doesn't make a lot of sense, right? But we're just kind of getting a sense of, well, how much does that need to be? I think, therefore, it's 20 inches long, right there, right? And therefore, the force that does for that 25 pounds right there, right, for that, instead of the force that I picked at 25, let's go ahead and put this in here so we'll get the correct number, right, because we're going to need that in a second. So we'll go ahead and put that back in there and say that the F right there, right, negative F sine of 45 and 20 plus our 25 and 12 equals 0. So I'm going to write that this is a preliminary guess. It's a preliminary guess. Is there going to be a final guess? So if we do that, we end 25 times 12, boom, divided by 20, divided by the sine of 45, boom. It turns out, that's kind of funny. That turns out to be 21.21 pounds. All right, that makes sense. It's kind of funny. I just couldn't figure that in my head. Well, whatever. All right, so so now what we want to get is the bending loads that are going to be onto this thing. So we're doing the loads portion of this thing. So what kind of bending are we faced with right here? Well, we have bending that's going to be about the x-axis, and bending that's going to be about the z-axis. Right? This was drawn for about the y-axis. So if we draw this thing, right? So you see this thing. So let's draw it looking at the zy axis right here. So the FBD in the here's z and here's y is going to be looking like that right there, right? And then moving down to here. And it's right down here where we're going to care about the stress. So we need to figure out what the moment is going to be right down there. Now, from the location that we're looking at, we're going to have a component, and this is going to be the F, and that's going to be in the Z component of the F right there is coming in that direction. Right? So we're going to have a reaction that's right there. That's a reaction in the Z direction. We're also going to have a moment that's being placed onto this, right? It's being bent about the x-axis right here. So I'm going to call that moment mx right here. And that's going counterclockwise, so that better go clockwise. And then the sum of the moments about the x direction right here is going to be this fz, right? And so that fz is going to be this f times the cosine or sine of 45, right? So it's going to be, and that's positive, so it's 21.21 times, I'll say cosine of 45, right? Times this distance, right? So we need to make a decision, right? So part of this distance right here, that right there is c over 2, right? And this distance is a. Well, does it need to be that tall? Does it need to have the proportions? I said in the problem statement, does it needs to be something close to be approximately like the sketch, the proportions. But I don't think it needs to be that tall. Let's just make it a foot. Let's make A 12 inches long right there. Okay, so we're going to assume A is equal to 12 inches. We've just made a design decision right there. Therefore, that right there. So now we've made a decision. C is equal to 4, B is equal to 20, and A is equal to 12. Why? It seems like these are relatively good numbers. I don't know. It's not 100% true, but this is design. Got to make decisions. Okay, so that's let's see. So that's going to be 12 plus 2. So that's going to be 14, right? Because that's C over 2. Remember, the C was equal to 4 right there. And then so now we're going to have minus mx is equal to 0. So mx is equal to, and by the way, we actually could find a simpler way to do this in a second. No, I think we do need to do this. Anyway, we'll get back to this. So mx is going to be that 21.21 45 times the cosine of that, right? That ends up being 15 times 14. So we get, is that all there is? 210.0 inch pounds. Right? Let's go ahead and use up some more green paper. It's not that expensive. So this is going to be page 4. This is going to be 2 continued right there, right? And I'm going to now do the FBD. I fill out this top part later right here. I'll do it now. S. I almost make it fall. Don't even know what season it is. S21, ME470, homework 1. All right, FBD. Now we're going to do this one in looking at the, let's go the X, Y, right? So this X, Y, but let's turn it over to looking from this side. It's not going to kill anything right here. So here's X and Y. Right there. And looking through in here, it's going to have a component right there that's going to be the FX that's being placed onto the thing, right? Like look up in here and see what's happening right to there, right? But you can kind of see that it's going in that direction. And so it's going to have a reaction, RX, right in there. But it's also going to have a moment that's being placed right there at the point at where it's going to fail. And that moment is, see, that's going counterclockwise. This one better go this way. And this is going to be the MZ, right? And remember that this dimension right here was C, and that this dimension right here that we had is going to be A. And we just chose that to be 12. So we're going to, in a similar way, the sum of the moments about the z-axis. And we're going to say that we have fx, which is going to be, once again, 21.21, right? And I'll just say that it's time the sine of 45 this time, but it doesn't really matter. And then it's also going to be times 14, and then minus mz. And now we're going to say that mz, if you're looking back up onto this thing, you can see that nothing has really changed. So it too is going to be 210 inch pounds, right? So the moments that are acting onto the thing, I should also write out what the torque is going to be, because I didn't write out 20. What's 25 times 12 is going to be the torque. So 25 times 12 is 300, right? So the total bending moment is going to be the square root of 210 squared plus 210 squared. You should be able to do that in your head. Just multiply by the square root of 2, right? So 210 squared 2 times square root. So that's 297 inch-pounds is the bending moment, total bending moment, and the torque onto this thing is the 25 times 12, which turns out to be 300. So they're pretty close to each other in terms of the amount of that happening onto here. But we wanted to, we now have to go to the material selection. Once again, it's not the most crucial thing in the world. We don't need to make it out of some rare material. So picking out material for this shouldn't be too terribly difficult. We could pick the same thing we've been picking. Maybe we want to make it a little bit stronger, or a little bit stronger material, so it doesn't, we might do an iteration actually as part of this in the real world, and we'd like to say, well, they made the handle too big. All right, so if we had to pick if we pick too weak of material, the handle might get too big. So let's see. Let's pick something that's like a little bit more beef to it here. I like the annealed stuff. So let's make it at a 1040 annealed, right there, right? So we have a tensile strength of 75, yield strength of 51, and this is going to be based on yielding, right? So we're gonna let's go for AISI 1040 annealed. Maybe we don't want the thing to corrode. We might want to pick stainless steel, right? We could pick stainless steel if we wanted to. Let's just see. Let's just explore. Do we have some stainless steels in here? Of some metals. I don't see any stain. Oh, here we go. Stainless steel. 3 or 4 stainless steel is very common stainless steel, and it's got a yield of 40. That's an option. Maybe you want to go stainless steel because you don't want our wrench to rust or our crank to rust, right? So I don't know, but I already picked this one down here. I forgot to write down the results. What did I say it was? Short-term attention span here. Okay, let's see. That was 1040 annealed, and that was 51 KSI. So that's the yield strength is 51 KSI, and we have a safety factor of 3. Okay, so. And we didn't actually say this. We said that was one of our givens that we were supposed to have. Design the crank with a safety factor of 3 DET. I said make sure we said DET, distortion energy. That was my shorthand communication for the thing. All right, so we know that the allowable is going to be equal to the yield divided by the safety factor. So that's 51 divided by 3. 51, 3 divided right there. So we get 17. Should be able to do that in my head. KSI. We know that it's circular, right? So we can use circular cross section to help us, so we could write this out for a diameter right here. We know that the stress is going to be equal to that stress plus 3 times tau squared. We know that this is going to be equal to MC over I, but for a circular cross section that ends up being, I think it's 32 M over pi d cubed. Do we need to cover why we got that, the cross section of the thing? And then we also know that we have tau is TR over J. For circular cross section is 16 T over pi d cubed. So we can plug all those things in. Maybe I can, I won't put the numbers in just yet, right there, right? This is going to be the allowable. So we've set into this right here. So let's just put that right in there. Square root 32 m pi d cubed squared plus 316 t pi d cubed squared, right? But we're squaring something and then square rooting the thing, so we can take this out. I could just leave this right here. I could just leave this right in here because I did that calculation up here. But let me go ahead, because this will be similar to. We'll see it in a second what it's similar to. So we could take the 16 and the pi out. Is that true? 16 and pi. Is there anything else that we want to take out? Yeah, we could take out the d, the cubed, right? Is that true? I think so. Yeah, so we could take, because this d's get squared, but then else doesn't get squared. So we take it 16 pi d cubed, and then square root of, and then this becomes 2 that's inside there, so it goes 4m squared plus 3t squared. So I get it right. Can I do all of that? So I get d right there is going to be 16 times n divided by pi and sy, and then the square root of 4m squared plus 3t squared, all of that cube rooted. Yeah, I think that's true. So let me put all that stuff in there. And I have 16 times my 3 pi, and I want to make sure that this, I'll go 51,000. Square root of 4 times, this is 297 squared plus 3 times 300 squared, 1/3. There's the 1/3. And I have my diameter here. Let's see how that works out. 297 squared times 4. 300 squared times 3. Add them together. Take the square root. Multiply it by 16. Multiply it by 3. Alright, now we're going to divide it by pi. So where's pi? Where's pi? Pi. And divide, and 51,000. Divide. And now I'm going to take the cube root of the whole thing. So there's that, and it's raised to there. And I get 0.6184 inches. I think what we're going to make, let's go up, let's use fractional things, and let's go it up to 0.625 inches, right? I believe that's 5/8. Does that make sense? I think so. I could picture that as a 5/8 piece. So, last page here, page 5, Dr. Deal. We have the Spring 21 ME470, and this is homework 1. And we are now going to present the design of our crank. right? So this is to continued. Crank design. Now this is supposed to be a drawing that's meant for to go to the suppliers, right, or down to the machinists right here. So I'm going to make it pretty neat. We don't need to draw any other view than this right here. And the whole idea in this assignment is to try to start simulating it like you're an engineer. You are an engineer who is going to be given a task by your boss, and hey, get the guys down in the machine shop to build a crank for this mixing machine that we have, and make sure that it's here's the general things that it's got to do, right? I'll give you some ideas, some parameters, and then the rest of it is up to you. I think I wanted to, in my design, if I were, it isn't to scale, it isn't proportional, because that's supposed to be 12 inches and that's supposed to be 21. So I'm not going to be lazy about this. I probably should actually make this a scale drawing, right? So let me be a better steward by taking the moment. I know it makes the video longer, and probably no one's going to watch it beyond this. But let's think about what a scale might be. I have right on here, let's see, well, 21 is my, or 20 is my largest dimension right in there. Let's make it 4. All right, so multiply by 1/5. It's like 1/5 right here. Nobody's going to know but us. So here is going to be our dimension right there. There's going to be like I took 4, right? So this, the 5 times this is going to be here. So I have 1/5 a scale of it. So now if I have 4, I divide the 4 by 5 onto the thing, and it's only going to be 0.8 right here on the crank handle. This is interesting. By the way, when you're doing something along these lines, maybe you want to make some decisions that that's not going to be that doesn't even look right. So maybe we shouldn't do that, right? So here's going to be 2.4 right here, right? So 2.4 is going to be like right there. Okay, and then 0.625. If I divided that by 5, that's like 1/8 of a thing right here. So that's not. See, I'm taking a look at this. We might even build like a SolidWorks model out of this thing. And by the way, this thing is going to be bent. It's probably going to be bent out of. Probably take a rod and heat it up, and hopefully when we heat it up, that's going to mess up our annealing, right? So we have to take into consideration about the buildability of this thing. All right, so. And maybe this thing is too wiry looking. I don't know. But there you go, right there. Probably should have done a better job of that corner right in there. I'll just sketch it right here. And once again, I have my contacts in, so I don't see very well right here. So drawing this thing out. So here we had, this is 20 inches. Right here we had this as 4 inches. And right here we have this as 12 inches. And we could specify this as 0.625 inches diameter. Does that look correct? Material in, what do we say? We said it was 1040. I just dropped my ruler again. 1040 annealed. AISI 1040 annealed. And that annealed might be a bad idea, because they might make this by heating up a piece of stock and bending it. And by heating it up, they're going to get rid of the annealing. Although they might be okay if it's like it's going to be attached right in there. Are they going to weld it onto the thing? There's some buildability decisions. But anyway, here is the homework problem 2, the design. Using stuff that you learned in ME470 to try to accomplish a task. It's an important aspect. We will depart from doing this assignment here. There is a project where we have to do the frame, and you're going to have to make some decisions about how you go about and making picking the amount of the frame. Most of it is actually probably going to be SolidWorks work that you're going to have to take part in. So that's it for this video. I'm not sure how long it was. Maybe it was too long. Let's see. Another 37 minutes. Hopefully this doesn't take you more than an hour to do. But it is going to challenge you, because you probably haven't done too many decision-making things before.